All right, we're going to take a look at the second part of the fundamental theorem of calculus. And although there is some discussion about which is part one and which is part two, that's really insignificant. Just understand there are two parts to it. The part we've learned already is how to evaluate a definite integral. Right? It's the antiderivative of the integrand function evaluated at the upper limit minus that same antiderivative evaluated at the lower limit. This part talks about how to take the derivative of a function that's defined as a definite integral. And you can see that here, the derivative with respect to x of the definite integral from some constant a to a variable upper limit. In this case, it's just x, but it could be any expression or function of x upstairs, and the upper limit of f of t dt is equal to f of x. It's a really, really simple and incredibly powerful tool to use here. I'm just going to show you how it works here with a specific example. So big F of x is equal to that definite integral from the constant -4 to that upper limit of x of t minus 1 dt. So the way to show you this works is actually take the antiderivative with the first part of the fundamental theorem of calculus and then differentiate that antiderivative, and then you'll see the shortcut hidden in plain sight there. So in this particular case, the antiderivative of t minus 1 with respect to t would be 1/2 t squared minus t. Right? Now we're going to evaluate that at -4 and x, so it's the antiderivative at the upper limit minus the antiderivative evaluated at the lower limit. And when this all works out, that winds up being big F of x right there. Right? Now we're going to take that, and that's a pretty easy derivative to do by the power rule for derivatives. Right? We're going to wind up simply with x minus 1. Now, if you take a look here, that x minus 1 pairs up pretty well with the original integrand. And that is the beauty of this second part of the fundamental theorem of calculus. This is essentially how it's going to work. If your function is defined as a definite integral, and your lower limit of integration is a constant, the upper limit is some expression of x, then the derivative of the function is going to be the integrand evaluated at the lower limit, at the upper limit, times the derivative of the upper limit. All right, so let's just do some examples. You'll see this really quickly. Just make sure that it matches that form, where the lower limit is a constant, it doesn't matter what constant it is, and the upper limit is a variable term. All right, so we have that here. All we're going to do is replace the t in the integrand with the upper limit x and multiply by the derivative of the upper limit with respect to x, because that's the derivative that we're taking of the whole thing. But the derivative of x with respect to x is just 1. So you simply wind up with the original integrand evaluated at the upper limit. It's quite a powerful thing here. Let's do another example. Again, constant lower limit, check, -1. Variable upper limit, x. So this one's simply going to work out to be the square root of x cubed plus 1. And you're done. That's the derivative. Here's another one. Constant lower limit, variable upper limit. Right? All you do is rewrite the integrand. You just replace all the variables in the integrand with the variable expression in the upper limit. And if your upper limit is anything more than just x to the first power, you have to multiply by the derivative of the upper limit. You'll see that in just a moment. All right, here's another one. Constant lower limit, pi, variable upper limit, x. Just rewrite the integrand and replace t with x. You're good to go. But it has to meet those conditions. You have to have a constant in the lower limit of integration and a variable in the upper one. If it doesn't meet that, you still can potentially do the problem. You just have to make a couple of little tweaks to make it work out. So over here, take a look. We've got a variable in the lower limit, x, and then the constant is in the upper limit of integration. So that is not what we want here to match our form and to be able to simply rewrite the integrand by substituting in the upper limit. So what we're going to do here is we're just going to use properties of definite integrals to reverse the limits. Right? If I have the definite integral from a to b of f of x dx, that is equal to -1 times the definite integral from b to a. And that's what I've written out down here with this integral. It's just equal to -1 times that. Now the constant is in the lower limit and the variables in the upper limit so I can apply the second part of the fundamental theorem of calculus, and I have my answer. Just remember to multiply it by -1 when you're done. All right, so that's pretty straightforward. All right, here's another one where we have now x squared, more than just x in the upper limit. So this is what we were talking about before, where you have to multiply the setup that you get by the derivative of the upper limit of integration. So, right, we just replace the t in the integrand with the upper limit x squared, but then we have to multiply by the derivative of x squared, which is 2x. And generally, when you see things like this written out, the 2x is going to come first. All right, here's another one. Take a moment and try that out on your own. Fairly easy to do. And we substitute the x squared in for t, but t was already squared in that argument of cosine, so now I have to take x squared and square it. And of course, we're multiplying by the derivative of the upper limit of 2x. And again, we'll just write the 2x in front, and there's your answer. So the last type of problem here that I want to take a look at in the video is what happens when you have variables in both the upper and the lower limits of integration. It doesn't mean you can't do the problem. What it means is you essentially have to do a trick here. We're going to split this up into two integrals using some constant that happen to be between the limits of integration. If x and x squared in this example aren't the same number, there will be some number in between them. So what I can do is I can say, well, I'm going to go from x to that constant and write one definite integral there, and then from the constant up to x squared, I'll have another definite integral there. The sum of these two still adds up to the entire region you're covering in big F of x there, but now I've split it into two things, and I have a constant. And again, in the first definite integral that's highlighted in green here, the variable is in the lower limit, but I can do what I did in the previous example and reverse the limits of integration and make that the definite integral from c to x. I just have to put a negative sign in front of it. And when I do that, I'm going to move that one into the second place. So the definite integral from c to x squared will come first, and then I'm subtracting from that the definite integral from c to x. All right, and now I can apply the fundamental theorem of calculus part 2 to each one of these things. The first one has x squared in the upper limit, so I replace all the t's with x squared, and I wind up multiplying that by the derivative of x squared, which is 2x. And the second one is just x, so I replace all the t's in the integrand with x. I'm going to do a little algebra here and clean this up, and I wind up with this final answer here. So that last example is the one that could potentially throw you simply because you have the two variable limits of integration. I just want to show you if that happens in general, right? All you're doing here is you're going to have the integrand evaluated at the upper limit times the derivative of the upper limit minus the integrand evaluated at the lower limit times the derivative at the lower limit of integration. Now, that should be more than enough for you guys to understand the basics behind this. We're going to go over some examples later on in class with this, but I think you get a general idea of it. If you have any questions, please feel free to let me know.